joining me today for the first of the Arista 7130 revamped training sessions. This was originally taken from some great material written by Ben, the previous East Coast SME, and Vignesh, who's hopefully going to help me maintain this one. This is very much an introductory course. It's going to cover the three major aspects of the 7130 platform. Today, the Connect series, and then in the next two sessions, we'll cover MUX, MetaWatch, and the just MOS operating system as a whole. So first things first, one of the things that I really wanted to get included in these revamp material slides is a nice index. So you'll see here that each one of these links is actually clickable. It'll take you to the relative section. Additionally, we're putting common problems at the end of major sections where you might get a call about a particular MOS application install upgrade, and having a quick place to go to kind of see what some of the common issues are. That said, without further ado, let's back up just a little bit and talk about what is a MetaMaco and why did Arista acquire them. So the MetaMacos, or the 7130 series of devices, are referred to as layer 1 switches. Now, I have to admit, personally, I'm not a big fan of the term. Switching to me means layer 2 specifically. It means Mac learning, it means VLANs, and it means dynamic connectivity between hosts when you plug them in. You'll find that that is not the case with these devices. They don't dynamically learn anything. Everything is by configuration. But also they don't do MAC address space forwarding. They don't do MAC address learning. They don't understand the concept of an all Fs MAC address to flood traffic out other ports. None of that is built into this. These are strictly layer 1 devices. Now, that said, one of the things that made these devices kind of famous, especially when they were released, is their best-in-class products, specifically for the 4 nanosecond. Again, it says layer 1 switching. Now, that 4 nanoseconds means that the port-to-port latency for bits coming in and going out is down to 4 nanoseconds, which is crazy fast, unheard of previously. For comparison, I think a 7150 averages like 230, 250 nanoseconds. So much, much, much faster. I'm not going to talk too much about applications today, but the other major reasons why Arista picked up the MetaMaco platform was, well, they're a great team that are based out of Sydney, Australia, and I work with these guys all the time. They really are a great team. They also developed applications for FPGAs that can be installed in the switch. So these devices don't have ASICs like your typical modern day layer 2, layer 3 switches do. And in order to get some sort of programmability into them, they used FPGAs. And they realized that by doing it this way, they could maintain very, very fast port-to-port connectivity, even through the applications built in the FPGAs. So that second bullet point there is 45 nanoseconds for the MUX app. Another application that was built was the MetaWatch app, which was for timestamping, and specifically timestamping accuracy. And there are others that we won't be going into a whole lot of detail during these introductory courses, but just know that there are other applications that we've built, and it's also possible for customers to build their own. So aside from that, these guys were a great complement to our portfolio because in a lot of our high frequency trading customer deployments, we were actually sitting side by side with these devices. The high frequency traders would use the MetaMaco devices for their fast port to port, and they would deploy it alongside a 7150 for things like BGP and multicast and PTP boundary clocks and stuff like that. So this was a huge expansion opportunity for us with a bunch of major banks and stock exchanges, people that were really interested in this fast layer 1 port-to-port switching technology. Also had some unique complementary unique complementary processes with our DANs and telemetry integrations. Apparently, I can't speak today, so hopefully that improves over the course of this. But anyway, here's just a sort of diagram so that we can show what single hop latency has looked like over the past 15, 20 years. And you can see that it used to be much slower, right? 1200 nanoseconds is very different than the near zero that we're approaching now. I'm really curious to see how much faster it even could get at this point, at least from a layer one technology perspective. We're approaching that zero more and more and more. And one of the other big things that we show later is that a meter of fiber is 5 nanoseconds, right? And we're already beating that out. So I'm curious to see if that's going to improve, and if so, by how much. Are we going to start measuring this in picoseconds instead of nanoseconds, for instance? But without further ado, we're going to jump into the, I'm going to say original. I don't know that to be true, but I was, as I was learning this, I started with the no FPGA device. That means that this is just a cross point for that quick port-to-port functionality. So what can we do with that? And what does it mean? So all ports are bidirectional, but you should think of all of the traffic streams as unidirectional. Meaning if you plug a host into Ethernet 1 on your 7130, your host is going to be able to transmit traffic into the 7130, and that's where it dies. It doesn't do anything by default, even if you connect hosts to all of the other ports. Again, there's no such concept in this as broadcasting or unknown unicast traffic, because this is a layer one technology. So that means that in order for the data sent by host one to reach the other hosts connected to the device, you have to actually configure it. Now, that said, each port on the device can be configured to transmit exactly what's received on any other port. So that means that instead of traditional dynamically distributed broadcast or multicast traffic, you could, for instance, have a host connected on Ethernet 1. We'll say that that's where this is on my cursor, and this box kind of represents the 7130 platform. So we'll say Ethernet 1, this is what we're receiving, and so this blue line, we're going to transmit it out to interfaces, and we'll call this Ethernet 2 and 3, right? And so it's actually very easy and possible to do that. We're just taking this data in, and then we're not streaming that data out, we're replicating that data out any relevant port that we want. This also means that different SFP types can be used in tandem, because the 7130 is actually kind of breaking down the signal that's coming in and then recreating it on the way out. And it knows how to dynamically do that to convert between, say, a base LR and a 10 gig DAC. Forwarding happens at the bit level, right? This is layer one, so we're not sending in frames, we're not sending in packets, we are sending in bits. And then because of that, it's also possible to transmit, again, that one-to-many concept, one device out, or one device in, multiple ports out. And you can do that, several times over throughout the configuration of the box. Speaking of the boxes, so the typical deployments are 1648 or 96 port devices. 16 and 48 are 1 RU. 96 port devices are always 2 RU. These are unrestricted 1-to-1 or 1-to-N. You can do port replication, you can do mirroring, you can do tapping. We mentioned the bit for bit forwarding, right? Non-blocking. They do come with dual power supplies and fans. These have configurable airflow. We offer AC or DC. They're also 1+1 redundant. So if you lose a single power supply or a single fan, nothing wrong happens. The device continues to function. Gives you time to get in there and replace it. You'll also see a lot of connotation that these are a layer 1 plus switch. So what is that plus? That plus means that we're doing signal regeneration, right? We kind of talked about that. That's how we're able to convert between media types. It also means that we've got per port packet statistics. We can determine if it's a valid packet, an invalid packet. We maintain link state, for each connected host. So while the hosts might see them as a connection to each other, like this was a patch panel, we can see in both directions. And we can do eye diagrams for monitoring and troubleshooting signal quality. We can sniff the ports via the management system. We've got fully managed SFP plus interface diagnostics, so your light levels, temperature, voltages, all your typical DOM stuff. Media conversion, again, we talked about fiber to DAC, but also single mode to multi-mode. We've got dynamic patching and link management. So today, maybe host 1 and host 10 need to be able to communicate with each other. Tomorrow, maybe it's host 1 and host 15. You don't have to recable that. You can change that just via the config. And then there's a whole slew of industry standards that these things support for various management or other communication methods, from SNMP, LLDP, JSON, RPC is pretty interesting as a sort of like automation standpoint. You've got your NEFCONF, syslog, AAA, etc. So I talked about this earlier, how fast is layer 1 plus? And the answer is really, really fast. So 4 nanoseconds is our port-to-port on the MetaConnect series, and that is faster than a meter of fiber. A meter of fiber is 5 nanoseconds. Now, the skeptics out there might say, well, how did you test that? So we did, and we documented it in a white paper. We looped a whole bunch of fibers together, connected them to this like super accurate time stamping device. And then we tested removing sections of fiber to figure out, the delay that was added when you added in one of these segments of fiber, and then we compared that to the 7130, and that's how we got our values. Again, there's a big white paper on this, and you will find customers that are interested, so you'll find links to that later. Again, where does layer 1 plus sit? At kind of like the OSI model, all the way down at the bottom, right? Just at the very, very, very top of that physical layer is kind of where these devices sit. Remember, again, I repeatedly said that these are not layer 2 devices, which is where the data link layer is. And we'll talk about that more in a bit, because that gets a little confusing when we start getting into LLDP. But in the interim, one of the other things that is always worth pointing out is with these devices, you really, really have to think physically, and not just physically, but unidirectionally, right? If we're receiving traffic from host A and we want to send it to host B, we need to go to the port on host B and basically say, host B is interested in this traffic, kind of like the way multicast works. And then, if we want host A to be able to receive from a host B, we need to do the same over there. And so if we do this configuration between two, actual hosts in that hang off of 7130, as long as these guys are in the same network, now they know how to talk to each other, right? But what if you put 4 hosts? Well, in order to actually do this, again, there's no dynamic learning in a 7130. You need to legitimately have 3 NICs on each of these devices for 3 hosts to get or 4 hosts to all have unidirectional traffic with each other, right? And that's not feasible. So if you've got a customer that picked up one of these devices and they think it's super cool, they're going to get 4 nanoseconds port-to-port latency in their office workspace where they literally connect all of their users. It's really not going to work out for them. And I have seen that happen once. So that's where you bring in your traditional layer 2 switch, right? And I was wrong when I remembered the latency before, so I'm glad that we came to this slide. Comparatively, the 7150 series switch has a 350 nanoseconds port-to-port latency. So again, you can see that there's a massive difference between the two. But so this is what a customer kind of expects when you're talking about a switch being deployed in an office. So it's again, just an important takeaway that there's a very big difference between your traditional layer 2 switch and the 7130 series of devices. Here we have some examples with a cross point. Now, some people take to these cross point or matrices very well, and some people don't. So let me start first by saying If you like these, great. We have a show command on the switches. You can look at all of your inputs and outputs this way. If you absolutely hate them, like I do, I much prefer the running config. Both of them are very readily available. But an example of how this is going to look from a matrix standpoint, right? So this left column is what we're receiving and the bottom is what we're transmitting, right? So A is actually on here twice because there's what we receive from A and then what we transmit to A, and those are two different things. So in this, we're saying, okay, A is going to transmit to B, cool, and B is going to transmit to A. And there's our unidirectional traffic between these two hosts. How does that look in the config? Is over here on the left. Now, I find this much easier to just kind of take a glance at and figure out what's going on, but again, to each their own. So what else can you do, right? We talked about this before. You've got A is transmitting data, and what if you don't care about the return traffic? You just want to get the data that A is transmitting out to host B and C. Well, that's easy. A can transmit to C and A can transmit to B. We have that 1 to N functionality. And this is how that's going to look from a configuration standpoint or from a matrix, right? So we can see that what's received on A is getting transmitted out B and C. And we can see on the left in our configuration that ET2 and ET3 both have a source of ET1. So that source means what comes in on ET1, what comes in on A is what we're going to transmit out these two ports. And just a third example here. In this case, we actually want to tap the interesting traffic between A and B. And in this case, interesting means all, right? So how do we do that? We can say, here's A, here's the connection to ET1, right, in the cross point. And we're going to say that B and C, which are Ethernet 2 and 3, are interested in that traffic. B connects to our host and C connects to our tap server. So we'll, on Ethernet 2 and 3, say that they have a source of Ethernet 1. And then our tap server has a second physical interface, so we want to tap the return traffic as well. So we're going to say Ethernet 1, which is our A host, and Ethernet 4, our D connection here, are both interested in traffic that's being received on Ethernet 2, which is where B lives. So we have Ethernet 1, Ethernet 4, source Ethernet 2. Right, and again, here's how that looks in a matrix. Here's what we're receiving for A, going down to B and C, receiving from B, going down to A and D. Now, there are some alternative ways to configure this as well. Now, the big takeaway is in the running config, you're always going to see it down here in the bottom right where it's sourced. But if you want to configure things differently or a little quickly in some circumstances, you can edit that. So you can do the traditional interface ET1, source ET2, and vice versa. There's bidirectional. You could also do interface Ethernet 1, destination Ethernet 2. And this will actually put source Ethernet. Oh, this is a typo down here. All right, let me go up here. This will actually put source Ethernet 1 under the config for interface Ethernet 2 using this destination command here. Or if you want to just connect two interfaces, you can say connect interfaces Ethernet 1, Ethernet 2. And it will not use this config because this is a typo. It'll do this equivalent up here. So how do you troubleshoot this, right? Well, the good news is it's all pretty, relatively standard layer 1 troubleshooting. We talked about how this is layer 1 plus. So we have a whole slew of details that we can work with. There's RX up and has link, TX up and has source MAC. We can see the source MAC speed. Now you'll see here that I didn't just say that there's RX and TX up, right? RX up means that we're we're receiving from the device, there's light. And link means that we actually have a connection that's more than just light. So you'll actually see cases where you'll have RX up, but you might have no link. And we actually cover a specific scenario later, so I won't get too detailed in that now. TX up is good as well. That means that we're actively sending light out back to this host. And also that we have a source. Our source is MAC, which actually means local. Again, more details on that later. And our speed that we're doing there is 10 gig. Cool. We can see that this is a 10 gig base SR. The mode is SR. We're not doing any auto negotiation. You can see temp, volt, all your DOM stuff. You can also see packet counts, right? RX octets and RX unicast packets, or multicast or even broadcast packets. Same thing for transmit. We have all of our FCS alignment, RX runts, etc. All available right with the one command, show interface Ethernet, in this case 26. Right. We also have verbose outputs. This is mostly just used for the threshold values. So if you issue the command, you'll get the current diagnostics up at the top. But the really interesting thing that you get are your alarm high and low warnings for all of the relevant values. And since this does vary by manufacturer, and these devices were not originally manufactured by Arista, right? This was an acquisition. So we don't enforce Arista only optics on these devices. So you will see varying temperature thresholds as customers will have different SFPs that are installed. Aside from that, we can look just at interface counters, and we have a few different types of counters that you can look at as well. So the regular show interface Ethernet BLA counters will get you your standard array of RX octets, unicast packets, multicast, broadcast, as well as transmit for the same port. We also have bins, so we can determine how big the packet is. And we have verbose counters as well, which is a couple of slides down. Let me just make sure. Yeah, this all looks good. Oh, one thing of note, we do not drop errored packets, right? We will pass those packets with the errors as they are, but we will try and detect those errors, right? So going back to those FCS, runts, etc., we'll increment those counters, but ultimately we're going to pass that packet off as is to the interested host. At the end of the day, this is a functional patch panel, right? We're just doing layer 1 connectivity between devices. We're not trying to be a link partner. So that said, and talking specifically about errors, one of the more important ones to be able to find and understand the implications of are the PCS errors. These are physical coding sublayers. So you'll see these in verbose outputs as PCS 49 errors, and they indicate bit errors, right? So errors at the actual bit level that are coming in or going out. Depending on link utilization, sometimes you get a bit error that's in the gap between actual bits and they don't really do much of anything. But you do need to pay attention to if these are incrementing when you're observing various layer 1 related problems. They can lead to FCS errors, alignment errors. They can show up as runts. They can also trigger false start of symbols, which makes it look like actual data when it's not data that's being transmitted. All sorts of weird and quirky problems that these particular errors can generate. So how do you find them? Show interfaces counters verbose. And there's a reason why this slide exists, right? If it was just a show command and just a thing, it would take 10 lines of text to be able to show you the importance. But on the left-hand side here, that snippet of data is actually just a very, very small snip of what you get when you run this particular command, even on just a single interface, right? So on the left, we created the scenario where we sent exactly 2 packets from a device to a second device with the 7130 in the middle, and we made sure that those packets were not responded to. And in this scenario, what we wanted to detail was the difference between line MAC and host MAC values, because using this diagram in the upper right here, here's an individual link partner, just one. So the second partner sits somewhere on the other side of this cross point. And these 4 values all represent what we're sending and receiving from just this one link partner. So the line MAC RX is what we're receiving from the link partner before we do clock data recovery. And host MAC TX is what happens afterwards. So these 2 values should, in theory, be exactly the same. And then for return traffic, your host MAC RX means it's coming from the other device that's not actually depicted in this diagram in the upper right. It hits our clock data recovery. It goes out Ethernet 26 as line MAC TX, right? this concept, along with PCS errors, is really important when we're trying to figure out where exactly an error is. And that said, we have a much bigger document that details it down here in the bottom right. I'm not going to click them, but I highly recommend bookmarking the slides and going through some of the links to other material for those that are interested. And we also have an EOS Central article here. These are going to talk a lot about the various counters that you're going to see in this verbose output, right? And so this, again, this is a little bit more. It's still not all of the potential options that you're going to see with these outputs. But I brought it here to show you, how big it does get. Oh, and actually, these are two different interfaces. Oh, yeah, this was the scenario where we sent the two packets between, and we have that. Great. The other thing that I wanted to point out in this particular slide was our PCS, right? And you'll see that we don't just count out PCS errors, we also specifically call out PCS good frames. Again, it's important because these, if you're doing bit for bit forwarding, which is what the device does, bit errors end up being, kind of detrimental to the overall health of, what we're sending bidirectionally between our interested hosts. LLDP, right? So I alluded to this earlier. The device by default operates at layer 1, right? Which means we're not a link partner. We operate technically, for those that are really layer 1 familiar, around the PMA sublayer of layer 1, which is just below the PCS sublayer. And this is all very much below the link layer. So at this particular layer, there's no concept of packets or framing or addressing, et cetera. It's just bits, right? And so because of that, we don't actually form LLDP neighborships with the devices that we're connected to. Now, that said, it's possible for us to do it, but the only way to do it is when we set the source for a particular interface as MAC. Now, source MAC is kind of like the technical, like you can tell that an engineer came up with this and not someone who has good customer relations, because the alternative way to phrase this is source me, right? It's just saying to source the physical connectivity to the connected host from the 7130, meaning your if you have tri-mode SFPs and you've got auto negotiation, you're not negotiating with the host that's on the other side anymore. You're negotiating with me, right? That's what that source MAC is kind of indicating. It also means that we can set up the device to send LLDP out to that connected link partner, but that is the only way to do it. Now, that said, each interface can only have a single host or a single source. So if the source of a particular interface is the 7130, that means that that particular host is never going to receive actual traffic that's coming in on the other ports, because there's no dynamic forwarding. Right? The only data that it's going to be able to receive is from the MAC of the 7130, and there's nothing to send. So we're just doing that to keep the link up, to build an LLDP neighbor. Like, that's it. We do use this a lot for troubleshooting, though. So if you have hosts on each side of the 7130 and they're not able to bring their respective link up with each other through the 7130, we might use source MAC on both sides, see if the link comes up to try and figure out what's going on, if it's an issue with just one side, etc. That said, we can detect LLDP neighbors through the interfaces. So even though we're not participating, we can kind of snoop those packets that the connected hosts are sending to each other and build an LLDP table that way. Again, how do we do that from the actual configuration standpoint? If we wanted to be the link partner, we'd set source MAC under the relevant interface and we'd say LLDP transmit. Relatively straightforward there, right? Again, you're not going to see this deployed frequently. The one exception is maybe we're connected to a tap, right? A tap has no interest in sending traffic back to us. It's just interested in the traffic that it's receiving from us. I had that backwards earlier. That's fine. So that particular device, it's fine if we're doing Mac or LLDP learning and source Mac in that particular scenario. So common problems, right? Link partner is not coming up or is continuously flapping. So I did talk about this a little bit before. One of the easy things to do is set source Mac on both sides and see if the links come up and stabilize. If they do, sometimes what you'll actually see is the hosts are kind of waiting for the other to bring up their optic and become functional. And if each host is doing that, then neither one ever really comes up. So um, when we set the source as Mac, we make sure to transmit a valid signal no matter what's going on the other side, right? And so that's a really quick way to test out if this is an issue between the two hosts that are trying to go through this pseudo patch panel that is our device, or if there's an issue potentially with other things like light levels, right? So you should also always check those, right? If your light levels are bad, um, there's a good chance you're not going to bring the link up or it's going to come up with bad quality. Um, as for solutions, sometimes these devices have a way to permanently bring up the link regardless. So the thing that they're doing is using some sort of link detection to look for an incoming signal before they turn on their laser. In most cases where that feature exists by default, it's also usually something that can be disabled. So not too much problems there. And that, in our experience, has always kind of broken that deadlock so that the end-to-end hosts can connect to each other without an issue. Other things, so I mentioned this before, we don't drop packets while we're in the L1 pass-through. We're sending whatever we're receiving. So garbage in means garbage out. We also have no restrictions on the MTU size. Again, this works like a wire, so we can pass any packet sizes. Now, that said, the link partner might drop the packets and maybe the customer does a TCP dump on their connected server and they're saying, hey, we're not seeing it. So how do we actually prove our innocence? So we can leverage the counters that we have. And particularly with our verbose counters, we can get extremely specific in what we're transmitting down to connected hosts. But we also have bins for packet sizes, etc. We can do packet captures directly on the panel port. That can be lossy, right? There's low buffer and it doesn't work great. So we can do kind of the Linux way of packet capturing, and we can send one to many. Again, we talked about this earlier where we could tap interesting traffic. We can do that to ourselves to a management interface. So we have two physical management interfaces on some devices, 1 to 2. Management 1 and 2 are typically physical management, and they're 1 gig. 3 and 4 are sort of logical management interfaces. You won't see a physical spot for them, but they exist in the software, and there's an actual Intel NIC that's associated with them. And so you can copy traffic over to those management interfaces at 1 gig, or if you have them, a lot of the newer devices also have 10 gig management interfaces, management 5 and 6. So those are the ideal ones because these devices were really, really built and deployed around the concept of 10 gig interfaces. So whenever possible, you should use your management 5 and management 6 when you're doing packet captures. And so just like any other interface, you'd say interface MA5, no shutdown, source Ethernet, whatever, port you're interested in looking at the traffic. And then much like EOS, you can do a bash sudo TCP dump. You do have to throw in the sudo. But you throw in all of your regular flags that you're used to seeing, and you can see those packets traversing. And that is actually it for the first of the sessions. So there's going to be 2 more of these, assuming I can get my timing right. I think each one's going to be about 40, 45-ish minutes. Hopefully everything here was informative. And if you have any questions, feel free to give me a shout. Google Hangouts chat is also available. Not available, but I keep it on my phone. So even if we're completely different work hours, feel free to shoot me a message, shoot me an email, get back to you as soon as I can. Thanks a bunch, and we'll see you next time.